What if I told you that the chair you're sitting on doesn't actually exist until you look at it? That a single particle can be in two places at once? And that the act of observation doesn't just reveal reality, it creates it? What if the moon literally might not be there when nobody's watching? Welcome to quantum physics, where the universe plays by rules so strange that even Einstein refused to believe them, calling one phenomenon spooky action at a distance, and insisting that God does not play dice with the universe. But here's the twist. Every experiment we've ever conducted suggests Einstein was wrong. The universe does play dice. Reality is fundamentally uncertain. And the deeper we look into the fabric of existence, the stranger things become. Tonight, we're diving into the most mind-bending, reality-shattering discoveries in science. Discoveries that power your smartphone, promise to revolutionize computing, and suggest that everything you thought you knew about existence might be only probably true. Buckle up, because we're about to explore a world where particles tunnel through solid walls, cats can be simultaneously alive and dead, and space isn't empty at all. The birth of quantum weirdness, when physics broke. At the dawn of the 20th century, physics seemed almost complete. Newton's laws of motion had stood for over 2 centuries. Thermodynamics was perfectly tidy. James Clerk Maxwell had unified electricity and magnetism into elegant equations describing light as electromagnetic waves. It was a golden age of certainty, and some scientists genuinely believed all the big questions had been answered. Only a few odd bits remained to be cleaned up. Dust in the corners of a well-swept room, as they put it. One of those dusty corners involved a very simple idea. What happens when you heat an object? When you warm a piece of metal or a lump of coal, it glows. First red, then orange, then white, depending on temperature. This phenomenon, called black body radiation, seemed straightforward. Objects emit electromagnetic radiation when heated. Easy to observe, should be easy to explain. Except the math refused to cooperate. Classical physics, using well-established equations, predicted something bizarre. As a black body's temperature increased, it should emit more and more energy at shorter wavelengths, particularly in the ultraviolet range. The problem? This prediction led to infinite energy at high frequencies. A scenario so impossible and ridiculous it was nicknamed the ultraviolet catastrophe. No amount of tweaking could stop the classical equations from spiraling into nonsense. Reality simply didn't match the predictions. Something fundamental was missing. Enter Max Planck, a conservative German theoretical physicist with a reputation for careful thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview. But he was pragmatic. And when faced with the black body radiation problem, he did something quietly revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't be emitted in just any amount? What if instead it came in tiny, indivisible packets, like coins you can't split in half? These packets would represent the smallest possible units of energy. He called them quanta. This was a dramatic shift from the continuous view of energy held by classical physics. Instead of a smooth flow, energy would arrive in steps, tiny jumps that depended on the frequency of radiation. Planck even introduced a constant, now known as Planck's constant, approximately 6.626 x 10 hours 34 joule seconds, to describe the size of these energy packets. It was unimaginably small but mathematically elegant. When he plugged this idea into his equations, something amazing happened. The infinite energy problem vanished. The equations worked. They matched the real world perfectly. Planck had solved the ultraviolet catastrophe. And yet, he didn't quite believe it. In fact, Planck himself described his solution as a mathematical trick, a clever way to make the numbers behave, not a description of how the universe actually worked. He assumed future physicists would find a better explanation that wouldn't require such odd assumptions. Quantization to him was a temporary patch, not a fundamental truth. What he couldn't have known was that his trick would become the cornerstone of an entirely new way of thinking. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. This humble beginning, tucked into a quiet paper published in 1900, didn't shout its importance. There were no dramatic declarations, no sweeping pronouncements, just a small constant, a new way of thinking about energy, and a curious fix for a problem that refused to go away. From that point on, physics would never quite feel finished again. Einstein's photons. When light became particles, by the early 1900s, light was thought to be pretty well understood. Thanks to Maxwell's equations, scientists had conclusively shown that light behaved like a wave, an elegant ripple in the electromagnetic field. It bent around corners, bounced off surfaces, diffracted, and interfered just like any proper wave should. After Planck's introduction of energy quanta, most physicists assumed things would settle into a new, slightly adjusted normal. But then came a puzzle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect. Here's how it worked. Shine light on a metal surface, and electrons get ejected from the metal. The concept made sense. Light delivers energy. Energy kicks out electrons. No big deal. According to wave theory, increasing the brightness of light should increase the energy transferred to electrons. A brighter wave should shake electrons loose more effectively. That was the logical expectation. But that's not what happened. In experiments, scientists found something strange. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even very bright light did nothing at all. No electrons were ejected. But above that frequency, even dim light could knock electrons free with ease. The threshold was sharp, and it made no sense under classical wave theory. This little inconsistency became a full-blown mystery. Enter Albert Einstein. In 1905, a year often called his miracle year, Einstein published a paper that changed everything. To explain the photoelectric effect, he proposed something bold. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle, a tiny bundle of energy traveling in a straight line? Einstein suggested that light was made of individual packets of energy, which he called quanta of light, later known as photons. Each photon carried a specific amount of energy determined by its frequency. Energy, Planck's constant X frequency. If a photon had enough energy, it could knock an electron loose from a metal surface. If it didn't, no amount of photons, no matter how many or how bright, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. No matter how many you had, you weren't getting in. Einstein's idea built directly on Planck's earlier work, but went further. He wasn't just using energy packets as a mathematical trick. He was suggesting that light itself was made of these packets, not as a convenient fiction, but as a literal description of how light behaves. It was a revolutionary claim, and not everyone liked it. Many physicists clung tightly to the wave model of light. After all, light clearly exhibited wave-like behavior. It diffracted around corners and created interference patterns. If light was really made of particles, how could it also behave like a wave? Einstein didn't deny the wave nature of light. Instead, he proposed something stranger. Light was both a wave and a particle. It could act like one or the other depending on how you observed it. This duality wasn't just a weird trick of perception. It was fundamental to the nature of light itself. Imagine a beam of sunlight filtering through a window. It spreads and ripples like a wave, bouncing off dust and glass. But zoom in, way in, and you'd find tiny quanta of energy, each with its own frequency, knocking into atoms, changing the world one collision at a time. This idea of wave-particle duality is one of the strangest concepts in all of physics, not because it's complicated, but because it challenges the very categories we use to describe reality. In the classical world, things are either particles or waves, not both, not neither, and certainly not whatever they feel like being depending on the situation. But the quantum world doesn't ask permission to make sense. Einstein's photon explanation of the photoelectric effect not only matched experimental results, it did so beautifully. The energy of each photon depended on its frequency, exactly as Planck had suggested, and it neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't carry enough punch. The impact of this idea was massive. In 1921, Einstein received the Nobel Prize in Physics, not for relativity, as many assume, but for his explanation of the photoelectric effect. That's how significant this discovery was. Still, even Einstein found the quantum world uncomfortable. He famously resisted the more probabilistic interpretations that would follow in later years. But dice or not, the rules were changing. And at the heart of those changes was a strange truth. Light, the thing that illuminates our world, refused to fit into any tidy box. It came in quanta. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep us wondering and just enough to keep us unsure. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Because if light could behave this way, both continuous and discrete, both spread out and point-like, what else might be lurking in the quiet corners of the universe, waiting to break the rules? The double slit, reality's greatest magic trick. Imagine this. You set up a table, place a light source at one end, and cut two tiny slits in a piece of cardboard. You shine light through the slits and observe the pattern it makes on a screen behind them. Not exactly thrilling, right? And yet, in this humble arrangement, two holes and a bit of light, we find one of the most mind-bending experiments in all of science. The double-slit experiment has become legendary in physics, not because it's complicated. In fact, it's almost embarrassingly simple. But because what it reveals is anything but simple. Some physicists have joked that this is the most dramatic science experiment of all time, starring a flashlight and two holes in cardboard. Let's start with what we'd expect. In classical physics, waves and particles behave very differently. A wave, like water or sound, spreads out and interferes with itself. Imagine ocean waves passing through two openings in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that reinforce or cancel each other. That's interference, and it's well understood. Now imagine particles, like tiny rubber balls, fired at a wall with two openings. Some go through the left slit, some through the right. They don't overlap or interfere. On the screen behind the slits, you'd expect two clusters of impact points right where the slits are. That's particle behavior. Straightforward, no surprises. So what happens when you do this with light? When scientists first shone light through two slits, they expected it to behave like a wave, and it did. The light spread out and formed an interference pattern, a series of bright and dark bands on the screen, caused by wave peaks overlapping and canceling each other in specific places. So far, so good. Light, as Maxwell predicted, was behaving like a wave. But then, things got weird. Using very sensitive equipment, researchers turned down the intensity of the light source until it was firing just one photon at a time. Instead of a constant stream, individual particles of light made their way toward the slits one by one. Now you'd expect these lone photons to act like particles, each going through one slit or the other. If you wait long enough and collect enough hits on the screen, you should see two bright spots where the particles landed, just like those rubber balls. But that's not what happened. Even when sent through one at a time, the photons gradually built up the same interference pattern as before, a pattern that required waves interfering with themselves. But how could a single photon interfere with itself? Did it go through both slits at once? Was it somehow a wave and a particle at the same time? This was no illusion. The interference pattern persisted, suggesting that each photon had traveled through both slits simultaneously, like a ghost of itself, exploring every possible path before landing. If that wasn't enough to raise eyebrows, things got even stranger. Physicists decided to peek behind the curtain. They placed detectors at the slits to observe which path each photon actually took. Surely, they thought, we can just watch and settle this once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they looked, the interference pattern vanished. As soon as the detectors were turned on and the photons were observed, they stopped behaving like waves. They acted like ordinary particles again, landing behind just one slit or the other. No more interference, no more ghostly wave behavior. It was as if the very act of observing forced the photon to make a decision: go left or go right. No superpositions, no fuzzy in-betweens. Reality had been caught in the act and immediately straightened up and acted normal. Turn off the detectors and the interference returned. Turn them back on and it vanished again. The implications were staggering. It wasn't that measuring devices disturbed the photons. These were passive, non-intrusive setups. The issue wasn't how we observed, but that we observed at all. It seemed that the mere knowledge of the photon's path, the potential to know, was enough to collapse its wave-like behavior into a particle state. Reality, in a sense, cared whether it was being watched. This wasn't just a fluke or experimental error. The double-slit experiment has been repeated countless times with photons, electrons, even molecules made of hundreds of atoms. Always the result is the same. Left, unobserved, these particles act like waves and interfere with themselves. Observed, they behave like classical particles and fall neatly into line. And if that sounds unsettling, you're not alone. This experiment sits at the very heart of quantum physics, and it resists every effort to explain it in familiar terms. It suggests that, at the smallest scales, particles don't follow strict paths. Instead, they exist as a spread of possibilities, a shimmering cloud of potential outcomes. Only when a measurement is made does that cloud collapse into something definite. Some have tried to picture the photon as a wave that splits and reunites. Others prefer the language of probability, describing the wave function as a tool for predicting outcomes. Still others, in the many worlds camp, imagine each possibility branching into its own separate universe. But whatever the interpretation, the facts remain the same. Until we observe it, the particle doesn't seem to commit to any one state. What began as a simple test of light has turned into a profound mystery about the nature of reality itself. Is observation an active part of shaping the universe? Does information have power over existence? Is reality fundamentally uncertain until we ask it to reveal itself? These aren't just philosophical questions. They're scientific ones, rooted in experiment, measured and confirmed. The double slit experiment doesn't give us clear answers, but it does give us one powerful insight. The universe at its core is not a clockwork machine. It's a strange and shimmering tapestry woven from possibilities, and it responds in curious ways to our gaze. With two slits, a light source, and a screen, we've discovered that the universe winks at us when we're not looking and stands still when we are. Schrödinger's equation, the mathematics of maybe. In the world of quantum physics, if there's one piece of mathematics that's whispered through the entire theory like a secret spell, it's Schrödinger's equation. This isn't going to be a math lecture. No one needs to worry about partial differential equations. But this particular equation is different. It's not just a string of symbols scribbled on a chalkboard. It's the quiet heartbeat of the quantum world. Back in the 1920s, physicists were wrestling with how to describe particles that didn't seem to behave like particles at all. Electrons showed wave-like patterns. Photons acted like probabilistic ghosts. The old laws of motion, the ones Newton gave us, just weren't cutting it anymore. The universe needed a new kind of language. Enter Erwin Schrödinger. In 1926, he proposed an equation that described not just how particles moved, but how their wave functions evolved over time. It was elegant, compact, and shockingly effective. At its core, it tells a simple story. It describes how a quantum system changes. The key concept is the wave function, often denoted by the Greek letter psi, pause. Think of it like this. The wave function is a mathematical whisper that tells us everything we can know about a quantum system, where a particle might be, how likely it is to be there, how it's moving or might be moving. The wave function doesn't give us hard answers. It gives us probabilities. If you picture a particle as a little dot moving through space, classical physics draws a neat arrow showing its exact position and velocity. Schrödinger's world doesn't do that. Instead, it gives us a hazy, rippling cloud, a wave that says the particle is likely to be over here, but could also be over there, and maybe just a little bit up there too. This is where the magic happens. Schrödinger's equation lets us evolve this cloud over time. It shows how the wave function changes as the particle moves, though it's really more like how the possibilities of its position shift and flow. And when we measure the particle, when we ask, "Where are you?" that wave function collapses. Suddenly, The cloud disappears. We get a single definite answer. Here it is, right there, but only after we've looked. This wave-based view of reality is profoundly different from the mechanical picture of the universe that came before. Instead of particles tracing predictable paths like planets around the sun, we now see swirling fields of probability, full of uncertainty and ambiguity until observation pins them down. Let's make this more visual. Imagine you're blindfolded and standing in a room. Somewhere in that room is a quiet cat. You can't hear it or see it, but you can toss little balls and listen for the sound they make when they land. Over time, you start to build a picture of where the cat might be. Areas with higher chance, others with less. That mental map you're building, that's like the wave function. It's not a picture of reality as it is, but as it might be. Now imagine you could write an equation that tells you how your map changes over time. Maybe the cat likes to move toward corners or sit near warm objects. That equation would be your guide to where the cat is likely to be next. That's what Schrödinger did, except instead of cats, he was thinking about electrons. The equation itself is continuous and smooth. It allows these waves of probability to ripple and shift, just like water in a pond. It respects the underlying symmetries of nature, like energy conservation and time evolution. But it doesn't care much for certainty. It tells us what could happen, not what will happen. And what's fascinating is how beautifully it works. Physicists have used Schrödinger's equation to describe everything from the structure of atoms to the way molecules bond, from semiconductor behavior to superconductors. It even predicts exotic phenomena like quantum tunneling, where particles slip through barriers they shouldn't be able to cross. One of its most famous successes was explaining the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no one could fully explain why electrons around a nucleus settle into specific orbits rather than spiraling inward or wandering off. Schrödinger's equation revealed that electrons aren't whizzing around like miniature planets. Instead, they form standing waves, stable patterns of probability around the nucleus. These are the orbitals you may have seen drawn as soft clouds or shapes in textbooks. These clouds represent the real, measurable likelihood of where an electron might be found if you decided to look. These aren't orbits. They're presence zones, and they exist only because the electron isn't a simple particle. It's a ripple in a sea of probabilities. It's strange, certainly, but it's also beautifully consistent. Unlike some theories that need patches or caveats, Schrödinger's equation has aged like fine wine. It works. It has predicted, time and again, the behavior of the very small with astonishing accuracy. And yet it remains hauntingly abstract. You can't hold a wave function. You can't see it, but it's there, describing the ghostly potential of everything from an atom in your tea to the electronics in your phone. Then there's the philosophical side. What is a wave function, really? Is it a description of our knowledge, or is it an actual part of reality, something that truly exists until it collapses into one outcome? Different interpretations of quantum mechanics argue fiercely about this, but the equation itself doesn't take sides. It simply does what it does, quietly, reliably, and strangely. Even Schrödinger himself had mixed feelings. While he was proud of the equation, he disliked the idea that particles didn't have definite properties until they were observed. His famous thought experiment involving a cat, alive and dead at the same time, was meant as a critique of the very uncertainty his work had unleashed. He gave us the mathematics of quantum waves, then questioned what those waves really meant. Still, it's hard not to admire what he built. In a world that often demands yes or no, here or there, Schrödinger offered something gentler, a shimmer of maybe, a softly pulsing guide to what could be. His equation doesn't shout or command. It suggests, it flows, and in doing so, it reveals a version of the universe that's quieter, subtler, and far more mysterious than we ever imagined. At the tiniest scales, motion isn't always motion, position isn't always position, and certainty is more of a luxury than a rule. But thanks to one elegant equation, we can still find our way, gently, mathematically, through the haze. Heisenberg's uncertainty, the universe's built-in blur. In the classical world, the world of apples, bicycles, and bowling balls, you can know where something is and how fast it's going at the same time. It's not even a question. A radar gun clocks a car's speed while GPS tells you exactly where it is. No mystery, no contradiction. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced a principle so strange and so central to quantum mechanics that it still gives students and scientists pause. It's called the uncertainty principle, and it tells us that at the most fundamental level of reality, there are limits to what we can know. Specifically, it says this: the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Now, momentum is just mass times velocity. It's a measure of how much motion something has. In everyday terms, this principle sounds almost silly. How could knowing where something is make you unsure about how fast it's going? If you see a train pulling into a station, you know both its position and speed. Easy. But at the quantum scale, reality doesn't allow that kind of clarity. And this isn't about our measuring tools being clumsy or crude. It's not a matter of needing better technology. The uncertainty isn't in our instruments. It's woven into the fabric of the universe itself. Let's say you're trying to observe an electron. You want to know where it is and how fast it's moving. To do that, you might shine light on it. But light is made of photons, and photons carry energy. When one of those photons hits the electron, it changes the electron's motion. It's a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You'll definitely find it, but you'll also destroy it in the process. Still, Heisenberg's point wasn't just about disturbing particles. His principle is built into the mathematics of quantum mechanics. Even if you could observe without interfering, watching through some ghostly, non-intrusive means, the uncertainty would still be there. It's not a bug, it's a feature. At the heart of the uncertainty principle is the wave nature of particles. Imagine trying to locate a wave in the ocean. You can say where the crest is, but the wave stretches out in space. Similarly, a particle like an electron is described by a wave function, a spread-out cloud of possibilities. If the wave is wide and smooth, you can't tell where the particle is exactly, but you can estimate its momentum fairly well. If you narrow the wave to pinpoint the particle's position, the momentum becomes more uncertain. The wave gets choppy. It's a cosmic trade-off, and there's no way around it. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a tiny number, Planck's constant divided by 4p. That number is very small, so in our everyday world, the effect is negligible. You can measure the position and speed of a baseball to incredible precision without ever bumping into quantum limits. But at the scale of electrons, atoms, and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behavior of the world beneath our senses. If you try to trap a particle in a very small space to nail down its position, it starts to behave wildly. Its momentum becomes highly uncertain, and it can begin zipping around unpredictably. Try to pin it down further, and it resists even more. It's as though nature doesn't like being told exactly where things are. This is not an error in the machinery. It's a blur that can't be wiped away. One way to think about it is like trying to hold mist in your hands. The tighter you squeeze, the less you have. Open your hands a little, and more of it lingers. That's the delicate balance between knowing too much and being forced to let go of something else. In many ways, the uncertainty principle is a philosophical warning label on the quantum world. It tells us that knowledge has boundaries, not because of human limitations, but because of how reality itself is built. We're not dealing with tiny billiard balls rolling through space. We're dealing with possibilities, probabilities, and waves that refuse to be nailed down too tightly. This principle also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus of an atom, since opposite charges attract. But thanks to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there, its position would be perfectly known, which means its momentum would become infinitely uncertain. That would require infinite energy. Nature says no. So electrons hover, not because they want to, but because quantum rules won't allow anything else. The uncertainty principle creates a kind of built-in resistance, a gentle pushback against absolute confinement. This strange limit also has consequences for other pairs of properties: energy and time, or angular momentum and orientation. In each pair, increasing precision in one means surrendering certainty in the other. It's a universal truth at the quantum level. And yet there's something comforting about it too. Uncertainty in this sense is not chaos. It's not randomness run wild. It's a structured ambiguity, a kind of graceful fuzziness. It gives the universe its texture. It allows particles to tunnel through barriers, atoms to be stable, and chemistry to happen. Without it, reality might be too rigid to support life at all. So much of science has been about finding certainty, predicting, measuring, knowing. Heisenberg's insight flipped that desire on its head. He showed that some aspects of nature will always remain just out of reach. And that's not a failure. It's just how things are. In a strange way, the uncertainty principle invites us to make peace with not knowing, to sit quietly with the blur, and appreciate the softness of what lies beneath the surface. It's a reminder that the deepest truths are not always sharp-edged, but cloudy, rippling, and unresolved. And perhaps that's exactly why they're so beautiful. Superposition and entanglement, the heart of quantum computing. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails. A light switch is on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division of states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time, just hidden from you. Quantum systems don't work that way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you're not looking. Instead, it enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided. It isn't switching quickly between the two. It is genuinely, physically in a state that is both, until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face, and your measurement becomes real. But before you looked, it wasn't just unknown. It was both. That's a hard pill to swallow, and it's not just counterintuitive. It's deeply weird. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, rather than following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Each possible state, a spin pointing up or down, a photon going left or right, is part of the equation, and all those possibilities coexist until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a path. It's spread out, smearing itself across every possible route it could take. When you interact with it, that fog suddenly snaps into a single location, a specific outcome, like lightning illuminating one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states. And so, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Schrödinger was highlighting the absurdity of applying quantum rules to large objects. But the idea struck a chord. It painted superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all the weirdness, superposition is not a flaw in the theory. It's not some bizarre loophole that physicists tolerate. It's one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message, is encoded using combinations of these two states. Quantum computers use qubits instead. And a qubit, unlike a regular bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them, it's genuinely in a mixture of both. This means that a single qubit holds more information than a classical bit. And when multiple qubits are entangled, we'll get to that in a moment, they can represent a vast number of states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical ones. It's not magic, it's just math that plays by quantum rules. Problems involving complex systems, like simulating molecules or optimizing large networks, suddenly become tractable. And it all hinges on the ability of qubits to be in superposition. But there's a twist. Superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, Stray photons, vibrations, even air molecules can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing in the next room. The superposition vanishes the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They give us access to probabilities, not certainties, and ask us to rethink what it means to say that something is. Now, let's talk about entanglement. Arguably quantum mechanics' strangest phenomenon. Imagine you have two gloves, one left-handed, one right-handed. You put each in a separate box and send one to the other side of the world. You don't know which box contains which glove, but the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. It's not mysterious, it's just logic. The gloves were always one left, one right. But quantum entanglement isn't like that. Entangled particles aren't like pre-packed gloves. They're more like a pair of gloves that don't decide which hand they are until after you open one of the boxes. And whichever one you open first somehow tells the other how to behave, instantly, no matter how far apart they are. It's not just that the outcome is correlated. It's that the properties don't seem to exist until the moment you measure one of them. And the act of measuring one instantly affects the other. This is quantum entanglement, and it is one of the strangest, most baffling features of the quantum world. Here's how it works. When two particles interact in a certain way, by being created together, colliding, or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one, in a very real sense, affects the other, even when they're separated by great distances. Imagine creating two entangled photons whose polarizations are uncertain until measured. One might end up polarized vertically, the other horizontally. But they don't decide ahead of time who gets which. They stay in a shared quantum state, a superposition of all possibilities. Only when you measure one does the outcome become definite. And at that moment, the other state becomes definite too, instantly. No signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say it's in Tokyo, responds at that very moment as though the universe just updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the idea that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate outcomes instantaneously without exchanging a signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows for such instantaneous connections, it must be missing something, some hidden variables tucked behind the scenes, determining the outcomes all along. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, Physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. When physicists performed these experiments again and again, quantum mechanics won. Entangled particles do behave in ways that can't be explained by local hidden variables. The results are random, yet perfectly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerie perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and thankfully, nature prevents it. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what results you get when you measure your particle, which means you can't encode information in it. The instant connection is real, but it can't be used for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow, when one person flips heads, the other always flips tails, and neither of them knows which it will be until they flip. They aren't sending messages, they're just in sync in a way that defies space. What's truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would remain. There's no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to uphold quantum theory. But what exactly is entanglement? Is it a kind of invisible tether? A shared identity across space? A subtle form of information smeared between particles? The truth is, no one's completely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deep, non-local fabric to reality. There's even a school of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time themselves. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If that's true, entanglement isn't something that happens in space, it's what holds space together. That's a bold idea, and one still under investigation. But it hints at just how central entanglement may be, not just to particles, but to the nature of reality. And like many quantum ideas, it's not just theoretical. Entanglement has practical applications. Quantum teleportation, not the Star Trek kind, but the real-world transfer of quantum states from one place to another. Quantum cryptography, a method of secure communication that guarantees privacy. If an eavesdropper tries to intercept the key, the entanglement is disturbed and the interference is immediately detectable. Quantum computing. Entanglement allows for complex operations involving many qubits that can't be reduced to simple individual actions. It's part of what gives quantum computers their power, not just more speed, but more interconnection, a kind of parallelism that ordinary computers can't match. So this spooky action, once a source of deep unease, is now a cornerstone of cutting-edge technology. Einstein may have disliked it, but even he couldn't deny its mathematical consistency. Entanglement reminds us that the universe is not simply a collection of independent objects bouncing around. It is a deeply interconnected web, where even distant elements can be parts of a shared whole. where separateness is, at times, an illusion. It's not something we see in daily life. You don't wake up entangled with your neighbor or find your coffee reflecting the state of someone else's spoon. But at the tiniest levels, this silent partnership between particles is quietly humming away everywhere, all the time. And maybe that's the strangest part of all, that even in a universe of stars and silence, of vast distance and emptiness, there are still echoes of togetherness, instant, invisible, and unshakably real. Quantum tunneling, walking through walls. In the everyday world, walls are pretty straightforward. If you throw a tennis ball at a wall and it doesn't have enough energy to get through, it bounces off. Simple, predictable. The universe says, "Nice try," and your ball obeys the rules of classical physics like a well-behaved object. But in the quantum world, predictability takes a holiday. In this strange realm, a particle can hit a wall, not have enough energy to pass through, and yet still show up on the other side. No smashing, no breaking, no squeezing through cracks. It simply appears, as if it decided the obstacle wasn't quite as solid as it looked. This phenomenon is called quantum tunneling, and it's one of those effects that makes you blink, rub your eyes, and wonder if the laws of physics are having a laugh. But tunneling is very real. It's measurable, predictable, and fundamental to how the universe works. And surprisingly, it all comes down to probability. To understand tunneling, we need to revisit the concept of wave functions. In quantum mechanics, particles like electrons aren't just little dots zooming around. They're described by wave functions that represent a spread of possible positions. These waves can extend across space, fading gradually instead of stopping abruptly. This means that even if there's a region the particle technically shouldn't be able to reach, the wave function might still stretch into that forbidden zone, albeit faintly. Now imagine a particle approaching a barrier, a region with more energy than the particle itself has. In classical physics, this would be a hard stop, game over. But the quantum wave function doesn't vanish at the barrier. It tapers off, like a whisper fading through a wall. And if the wall isn't too wide or too tall, that whisper can make it to the other side. The particle might not have enough energy to climb over the barrier, but its wave function can tunnel through. And if part of the wave function makes it to the other side, there's a small but non-zero probability that the particle itself will show up there too. It's not magic, it's math. This idea sounds abstract, but it has very concrete consequences, especially when you shrink your thinking down to the atomic scale. Take radioactive decay, for example. Some atomic nuclei are unstable, and one of the ways they become stable is by ejecting particles, like alpha particles, made of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a powerful nuclear barrier. According to classical physics, they don't have enough energy to escape. But they do escape, constantly, and quantum tunneling is the reason why. Inside the nucleus, the alpha particle's wave function stretches toward the edge of the nuclear potential barrier. Even though it's unlikely, there's always a chance the particle will tunnel through. Over time, that small probability adds up, and eventually the particle pops out. That's radioactive decay in action. Without tunneling, many elements would never decay, and nuclear physics as we know it would grind to a halt. Tunneling is also critical for the most important energy source in the universe, nuclear fusion. In the cores of stars, hydrogen nuclei are crushed together under immense pressure and heat. But even with those extreme conditions, they don't really have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does. Yet stars shine, and tunneling explains why. At those high temperatures, hydrogen nuclei get close enough for their wave functions to overlap. There's a tiny chance that one will tunnel through the repulsive barrier and fuse with another. Multiply that tiny chance by the unthinkable number of particles in a star, and you get a brilliant, sustained fusion process, the furnace that powers everything from sunshine to supernovas. And it's not just distant stars that benefit from tunneling. We use it right here on Earth, in labs, in factories, even in experimental computers. One elegant example is the Scanning Tunneling Microscope, STM. This device allows scientists to visualize surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip extremely close to the surface of a material, just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By measuring this tunneling current, the microscope builds up an incredibly detailed map of the atomic landscape. What's remarkable is that the STM doesn't touch the atoms. It's imaging entirely by relying on tunneling, on the ability of electrons to slip quietly through empty space, across a gap, and into a detector. This non-contact technique gives scientists a way to peer into the quantum terrain with stunning precision. Tunneling is also at the heart of certain types of electronic components, like tunnel diodes and quantum dots. And it's a looming factor in the future of computing. As we shrink transistors to ever smaller sizes, we're running into quantum limits. At nanometer scales, electrons can tunnel through barriers that were once considered solid. It's as if the walls in our circuitry are starting to let particles sneak through when they're not supposed to. This presents both challenges and opportunities. On one hand, it creates noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling rather than fight against it. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as made of hard boundaries. A particle can go here but not there. A wall is a wall, but the quantum world is more nuanced. Barriers are not impenetrable. They are probabilistic. They are suggestions, not absolutes. And while we might find that unsettling, it's also strangely elegant. Because of tunneling, particles are not confined to the straight paths we imagine. They can cheat, slip, blur through the cracks of logic. They remind us that the universe is not a machine made of perfect gears, but a shimmering tapestry of likelihoods and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they might just glance at that same wall and say, "I think I'll take the shortcut." And somehow, nature lets them. The quantum vacuum, when nothing is everything. In everyday life, we think of nothing as, well, nothing, the absence of stuff. An empty room, a blank sheet of paper, the space under your bed where socks mysteriously disappear. When we extend that idea to physics, we often picture the vacuum of space as a perfect void, a cold, silent expanse with absolutely nothing in it. But in quantum physics, nothing is never really empty. What we call the quantum vacuum is a restless, jittering stage. It's not filled with atoms or light or sound, but it's far from blank. Even when all particles have been removed and no fields are actively doing anything, the vacuum still seethes with energy. At the smallest scales, space is alive with invisible activity, waves rising and falling, particles flickering in and out of existence. It's like the hum beneath silence, the glow behind darkness, and it all starts with uncertainty. Heisenberg's uncertainty principle doesn't just apply to particles' position and momentum, it also applies to energy and time. That means that even in a region of space where energy should be zero, the energy can briefly fluctuate. These fluctuations give rise to virtual particles, which appear spontaneously, hang around for a fleeting moment, and then vanish as if they never existed. They're called virtual, not because they're imaginary, but because they can't be directly observed, only inferred through their effects. These quantum blips might seem like a mathematical curiosity, but they have very real consequences. One of the most striking examples is something called the Casimir effect, one of those rare phenomena that lets us see the quantum vacuum doing something tangible, something measurable. Here's how it works. Imagine placing two very thin, perfectly conducting metal plates extremely close together in a vacuum, just a few nanometers apart. According to classical physics, nothing should happen. There's no air between the plates, no forces acting on them, just an empty gap. But quantum mechanics says otherwise, because the space between the plates is so small, only certain wavelengths of virtual particles can exist there, ones that fit neatly between the boundaries. Outside the plates, however, there's no such restriction. The result? There's slightly more pressure from virtual particles outside the plates than between them. And this imbalance creates a force that pushes the plates together. That's the Casimir effect. It's a tiny force, but it's been measured. In precise laboratory experiments, scientists have observed these plates attracting each other exactly as quantum theory predicts. It's as if the vacuum itself is gently squeezing them, proving that even nothing has a kind of substance. This vacuum energy isn't just limited to quirky lab setups. It plays a role across the entire universe. In cosmology, there's the idea of vacuum energy density, the notion that the energy of empty space might be responsible for the accelerating expansion of the universe. We call this mysterious force dark energy. And while we don't fully understand it, the concept of a quantum vacuum buzzing with energy might be a big part of the puzzle. But there's a catch. The predicted energy of the quantum vacuum, according to quantum field theory, is enormous. If we tried to calculate the total vacuum energy of the universe using what we know from particle physics, we'd get a number that's wildly larger, like 120 orders of magnitude larger, than what we actually observe. This is often called the worst prediction in physics, and no one has quite figured out how to fix it. But it highlights just how complex and surprising the vacuum really is. Back at the quantum scale, virtual particles also play a supporting role in other strange phenomena. In quantum electrodynamics, for instance, the interaction between charged particles is partly mediated by the constant exchange of virtual photons. These exchanges give rise to the electromagnetic force as we experience it. Even the mass of particles like protons is affected by the swarm of virtual quarks and gluons flickering around inside them. What we think of as stable, solid matter is really the result of constant interactions with this invisible, fluctuating vacuum. And while these particles appear and disappear faster than we can measure, Their influence is everywhere. They slightly alter the energy levels of electrons in atoms. They contribute to the magnetic moment of particles. They're woven into the fabric of every interaction in nature. This might sound like science fiction, but it's been tested. When we correct our calculations to include vacuum fluctuations, like in the famous Lamb shift observed in hydrogen atoms, we find that the predictions match reality with breathtaking accuracy. The math is weird, the concepts are wild, but the results are solid. In a way, the quantum vacuum is the most fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, exists within it. They ripple and hum against its background, like instruments playing on top of a bass line that never stops. Some physicists even suspect that the vacuum holds clues to deeper truths. Could it be the source of all structure in the universe? Might it contain information about quantum gravity or even about space-time itself? These are open questions, but one thing is clear. The vacuum is not a passive backdrop. It's active, it's structured, it's full of potential. Even in the coldest regions of space, where matter is scarce and starlight is a memory, the quantum vacuum is still there, vibrating, jittering, whispering the rules of existence to anything willing to listen. It's humbling to think that nothing is never truly nothing, that even in apparent stillness, the universe teems with hidden activity. In the pauses between moments, in the gaps between particles, in the silence between stars, something is always happening. We live not on a quiet stage, but on one that murmurs beneath our feet. And while we may not hear it with our ears, physics has found the instruments to listen. The vacuum hums, the particles flicker, and reality dances to a rhythm we've only just begun to understand. Quantum biology, life's quantum tricks. In the world of quantum physics, we expect things to be strange. Subatomic particles teleport through barriers, spin in two directions at once, and form entangled pairs that whisper across the cosmos. But there's a place we usually don't expect to see quantum behavior: biology. Biology is messy, warm, and wet. It operates in a noisy world full of jiggling molecules, random collisions, and fluctuating energy. Quantum effects, on the other hand, are notoriously fragile, easily disrupted by heat and chaos. That's why we build quantum computers in freezing cold labs and isolate particles in high vacuum chambers. And yet, somehow, life seems to be using quantum tricks of its own. Take the robin, for example, a small, unassuming bird with a surprising sense of direction. Robins are migratory, flying thousands of miles with uncanny precision. But what's guiding them? How do they know which way is north? Scientists long suspected that birds had a built-in compass, but the details remained elusive. Then came a radical idea: quantum entanglement might be involved. The hypothesis goes like this. Inside a bird's eye, there may be a protein, likely called cryptochrome, that contains a pair of entangled electrons. When light hits the molecule, it excites these electrons, causing them to become quantum linked. Their entangled spins then interact with Earth's magnetic field, influencing a chemical reaction in a way that depends on the direction the bird is facing. If that sounds like science fiction, you're not alone. The idea was met with skepticism. Entanglement is delicate. Could it really survive inside a living cell, among churning proteins and bustling water molecules? Surprisingly, early experiments suggest it might. There's growing evidence that birds really do rely on a quantum process to detect magnetic fields. It's not yet fully proven, but the signs are promising. If true, it means nature has figured out how to preserve quantum information in a biological setting, something human engineers are still struggling to perfect. Now let's shift to something green and leafy. Plants. Like birds, plants are masters of a subtle quantum game. Consider photosynthesis, the process by which plants turn sunlight into chemical energy. It sounds simple enough. Light hits a chlorophyll molecule, which absorbs the energy and transfers it to a reaction center where it's stored. But how does that energy get there so efficiently? You might think it hops randomly from molecule to molecule until it reaches the right spot. That would be slow and clumsy. But measurements suggest something far more elegant is happening. The energy appears to explore multiple paths simultaneously, as though the system is using quantum coherence to find the most efficient route. Imagine dropping a marble onto a maze. Instead of rolling down one corridor, it spreads out like a wave, feeling every possible path, then settling on the shortest. That's how some researchers believe photosynthetic complexes behave. The energy doesn't wander aimlessly. It takes the best route, thanks to a bit of quantum navigation. This is astonishing because these systems are warm, biological, and noisy. Yet quantum coherence seems to persist long enough, sometimes on the scale of picoseconds, which in the world of molecules is a decent stretch of time, to influence outcomes. If plants are quantum strategists, it raises a tantalizing possibility. Has evolution learned to harness quantum mechanics? There's no reason to think biology can't make use of the same principles we find in physics labs. After all, nature had billions of years to experiment, and organisms that found clever quantum shortcuts, whether for energy efficiency, navigation, or sensing, may have enjoyed a survival advantage. Speaking of sensing, there's one more biological mystery that might have a quantum answer: the sense of smell. We usually imagine that smell works by shape. A molecule fits into a receptor in your nose, like a key fitting into a lock. And voila, you detect the scent. But that theory has some holes. Molecules with similar shapes can smell wildly different, and some molecules with different shapes can smell exactly the same. One alternative idea is the vibrational theory of olfaction, which suggests that our noses don't just detect shape, they detect how molecules vibrate. The proposal is that when a molecule binds to a receptor, electrons in the receptor might tunnel through the molecule, and the likelihood of tunneling depends on the molecule's vibrational frequency. If true, it would mean that part of your sense of smell involves quantum tunneling, the same trick that lets particles pass through barriers in nuclear fusion. Your nose might be sniffing in stereo, both structurally and vibrationally, using quantum mechanics to help decode the invisible world of molecules. Again, the idea is controversial, but experiments have shown that people, and even fruit flies, can sometimes distinguish between molecules that differ only in vibrational frequency. It's not conclusive, but it's enough to keep scientists intrigued. Quantum biology is still in its infancy. Most of the field is built on bold ideas, tentative experiments, and more questions than answers. But what makes it exciting isn't just the novelty, it's the reminder that the strange rules of quantum physics don't stop at the lab bench. They reach into the feathers of birds, the leaves of trees, and the breath you draw through your nose. It's a humbling thought. The same mathematics that describes the behavior of electrons in a vacuum also underpins the chirping of a robin and the shimmer of sunlight on a leaf. Nature doesn't separate its domains. Quantum effects aren't locked away in some microscopic vault. They're everywhere, woven into life itself. And perhaps, as we learn to understand these quantum tricks, we'll gain not only new technologies, but a deeper appreciation for the ingenuity of evolution. Life, it seems, has always been playing with the strangest tools in the universe. They just never bothered to tell us. The big questions, what we still don't know, despite quantum mechanics' stunning success, its breathtaking precision, its technological applications, its revolutionary insights, profound mysteries remain. These aren't just gaps to be filled in, they're fundamental questions about the nature of reality itself. What causes wave function collapse? This is perhaps the biggest mystery in quantum mechanics. We know that before measurement, a quantum system exists in superposition, a blend of all possible outcomes. We know that after measurement, it settles into one definite state. But what exactly triggers this transition? Is it the physical act of measurement? The transfer of information? Consciousness? Interaction with the environment? Different interpretations offer different answers, but none is proven. The Copenhagen interpretation says measurement causes collapse, but doesn't explain what counts as measurement. Many worlds eliminates collapse entirely by proposing infinite branching universes. Objective collapse theories suggest spontaneous collapse according to unknown physical laws. But the truth is, we still don't know. Is reality fundamentally uncertain? Or are there hidden variables? Quantum mechanics predicts probabilistic outcomes. When you measure a particle, the result is genuinely random within the constraints of probability. Einstein believed this meant the theory was incomplete, that there must be hidden variables determining outcomes beneath the quantum surface. But Bell's theorem and subsequent experiments suggest there are no local hidden variables. The randomness appears to be real, not just a reflection of our ignorance. Yet this raises deep questions. If outcomes are truly random, what does that mean for causality? For determinism? For the fabric of reality itself? How do we unify quantum mechanics and gravity? Quantum mechanics describes the very small with incredible precision. General relativity describes gravity and the very large equally well. But the two theories are fundamentally incompatible. Quantum mechanics is probabilistic and operates in flat space-time. General relativity is deterministic and describes curved space-time. Attempts to merge them through string theory, loop quantum gravity, and other approaches remain speculative. We don't yet have a working theory of quantum gravity, and until we do, our understanding of the universe remains fundamentally incomplete. Where does quantum weirdness end? The double-slit experiment works with electrons, atoms, even molecules made of hundreds of atoms. But where's the boundary? Could we ever put a virus in superposition, a bacterium, a cat? Where and why does quantum behavior give way to classical behavior? Decoherence offers partial answers. Large systems interact too strongly with their environment to maintain quantum coherence. But it doesn't fully explain why we never observe macroscopic superpositions. The boundary between quantum and classical remains fuzzy and fascinating. Why this particular quantum universe? Why do we have these specific particles, these forces, these constants? Why does the universe follow quantum rules at all? These are questions quantum mechanics doesn't address. It describes how the quantum world works, but not why it exists, or why it has the particular properties it does. Some hope a theory of everything might answer these questions. Others suggest they may lie beyond the reach of science, in the realm of metaphysics or philosophy. What is the relationship between quantum mechanics and consciousness? Some interpretations suggest that observation, perhaps conscious observation, plays a fundamental role in quantum mechanics. But what does that mean? Does consciousness collapse wave functions? Is consciousness itself a quantum phenomenon? Or is this a red herring, conflating measurement, a physical interaction with awareness, a subjective experience? These questions touch on the deepest issues in philosophy of mind and may not have purely physical answers. Despite these mysteries, quantum mechanics remains spectacularly successful. It's been tested to extraordinary precision. It powers modern technology. It's revealed profound truths about reality, but it's also shown us the limits of our understanding, and perhaps the limits of what can be understood. And maybe that's okay. Maybe the universe is under no obligation to make complete sense to creatures evolved to chase prey across savannas. Maybe mystery isn't a bug, it's a feature. Conclusion: living with the quantum. We've journeyed through a strange and beautiful landscape tonight, from Planck's reluctant quanta to Einstein's troublesome photons, from the double-slit surveillance-sensitive particles to Schrödinger's equation of maybe, from Heisenberg's irreducible blur to superpositions that refuse to choose, from spooky entanglements to particles that walk through walls, from a vacuum that isn't empty to birds that navigate by quantum compass. Along the way, we've discovered that reality at its deepest level is nothing like we imagined. It's not made of tiny billiard balls following predictable paths. It's not a clockwork mechanism ticking away according to iron laws. It's something stranger, softer, more beautiful. It's a shimmering field of possibilities that only crystallizes into definite form when observed. It's particles that are also waves and waves that are also particles. It's connections that transcend space, uncertainties that are fundamental, and a vacuum that seethes with invisible energy. Quantum physics teaches us humility. It shows us that our common sense, intuitions, built for navigating a world of medium-sized objects moving at medium speeds, don't apply at the smallest scales. Reality is under no obligation to make sense to us. And yet, through patient observation, clever experimentation, and elegant mathematics, we've managed to glimpse its strange inner workings, and what we've found is breathtaking. Quantum mechanics isn't just abstract theory. It powers your smartphone, enables MRI machines, promises to revolutionize computing and cryptography. It explains why atoms are stable, why stars shine, why chemistry works the way it does. More than that, it offers a profound shift in perspective. Uncertainty isn't a flaw to be overcome. It's the texture of reality itself. Randomness isn't chaos, it's structured possibility. Observation isn't passive, it's participatory. We're not separate from the quantum world. We're made of it, woven from the same fields and forces. You are a pattern in the electron field, the quark field, the photon field. Your thoughts are quantum excitations. Your existence depends on tunneling, on superposition, on entanglement. You don't end at your skin. The fields that define you extend outward, fading gradually into the broader quantum sea. Perhaps the most important lesson isn't about particles or probabilities, but about perspective. to embrace uncertainty, not as failure, but as feature, to see that reality is richer and stranger than we imagined, not a single story, but a vast library of possibilities, not a finished canvas, but a work in progress, not a closed book, but an open question. Quantum physics doesn't give us all the answers, but it gives us something more valuable: wonder, a sense of awe at the universe's profound strangeness, a reminder that beneath the familiar surface lies something deeper, something that shimmers and shifts, something that dreams. The universe, it turns out, is not a machine. It's a symphony of possibilities, a dance of probabilities, a poem written in the language of mathematics. And we, fragile, curious, briefly conscious arrangements of quantum fields, get to witness it, explore it, and marvel at it. So, as you drift off tonight, remember, until you observe it, reality is just probability. Particles exist in superposition. The future is unwritten, and maybe, just maybe, that's exactly how it should be. Thank you for joining this quantum journey. Whether it kept you awake or helped you sleep, I hope you found something worth wondering about. Because in the end, that's what quantum physics offers: a universe that's stranger, more beautiful, and more full of possibility than we ever dared imagine. A universe that, in its deepest heart, dreams too. Good night. And remember, somewhere in the quantum foam of empty space, virtual particles are flickering in and out of existence. Somewhere, entangled particles are coordinating across cosmic distances. Somewhere, an electron is tunneling through an impossible barrier. And somewhere, a wave function is collapsing into reality. The quantum world never sleeps, but you should. Sweet dreams.